Tonight, drift into the luminous darkness around one of the strangest stars in our galaxy. In this video, we wander through the blue storms of AG Carinae, follow its slow-motion eruptions, and rest inside the vast dust bubble it has carved into space. Let the calm storytelling and gentle cosmic imagery carry you toward deep sleep, while your mind quietly explores the life and fate of this unstable giant. If you enjoy science that soothes you to sleep, please remember to like this video and subscribe for more cosmic sleep documentaries. In a quiet corner of the Carina constellation, a deep blue star rests inside a pale sphere of gas and dust. This object is AG Carinae, a massive star balanced near the edge of slow explosion wrapped in a bubble that preserves the story of its outbursts. Around it, the wider spiral arm of the galaxy lies like a dim backdrop, while this one star and its shell form a small intense world of their own. From far away, the pair looks like a single point of light, yet inside that point space is carved into layers, ridges, and drifting filaments. At the centre, the star shines with a surface so hot that light presses outwards with almost as much insistence as gravity pulls inward. That tension gives the whole scene a feeling of suspension, as if everything is caught between settling and breaking apart. The nebula around AG Carinae spans roughly 5 light years from side to side, similar to the gap between the Sun and its nearest stellar neighbour. In that volume, space is not empty but filled with tenuous material thinner than most regions between stars, yet thick enough to glow when starlight passes through. Seen as a whole, the system resembles a bright lamp placed at the heart of a thin, smoky glass globe, with the glass traced by faint scars of past storms. AG Carinae belongs to a rare class called Luminous blue variables. Massive stern sailed a short, unstable phase close to the limit of their own brightness. In simple terms, it is a star that shines so strongly that its own light begins to push its outer layers away. A useful analogy is a reservoir filled close to the brim, where even a modest rise in level sends water sliding over the edge. In the same way, small changes in temperature or internal structure can set off episodes where the star throws material outward. These episodes do not resemble a sudden blast on short timescales. Instead, they unfold over years, then leave results that keep expanding for tens of thousands of years. The luminous blue variable stage matters because it is one of the last opportunities for a very massive star to reshape itself before its core finally collapses. Matter removed now will not be part of the compact remnant later, and the space around the star becomes seeded with elements that future generations of stars and planets can include. The bubble of AG Carinae is an example of a circumstellar nebula, a shell of gas and dust that forms around a single star through its own activity. In this case, part of the material is thrown off during violent eruptions, and part is swept into shape by the steady push of a powerful stellar wind. A convenient picture is of air streaming from a vent into drifting smoke, hollowing out a cavity and piling the smoke into a thin wall. Here the vent is the star, the smoke is older gas, and the wall is the visible shell. This shell is not smooth. It shows bright knots, darker gaps, and curved arcs that branch and twist. These structures form where flows of gas meet, compress, and cool, creating differences in density that later shape how light is emitted and scattered. The main number that sets the feeling of size here is that 5 light-year span. Light takes about 5 years to cross the bubble, while light crosses the orbit of Neptune in only a few hours, so the bubble stretches far beyond any planetary system scale. That contrast between neighbourhood size and bubble size is one of the first scale shifts in this story. Inside the bubble, dust grains form a delicate interior landscape. Tiny solid particles condense out of cooling gas and move outward with it like fine ash caught in a slow breeze. In some regions, the grains clump into thin sheet like structures that cast shadows on the gas behind them. In other regions, they gather into small clouds that trace the paths of past flows. Light behaves differently in each part. In one zone, it passes through almost unchanged. In another, it is scattered into a soft blue haze. Elsewhere, it is absorbed and re-emitted in longer wavelengths, turning some parts of the shell into gentle, warm glows, while other parts stay faint. These changes in brightness and colour hint at gradients in temperature and density across the shell, from inner edge to outer boundary. Despite this rich structure, there is a sharp limit to what direct observation can reveal. At this distance, many of the smallest knots and filaments blend together, falling below the resolution that any image can cleanly separate. Only by comparing models of how gas flows and cools with the overall pattern of light can the hidden fine detail be inferred. For intuition, the true slowness of the scene is also hard to grasp. Gas moves at speeds that would cross a planetary system in a single year, yet needs tens of thousands of years to cross the entire shell. The bubble is expanding, but it does so at a pace that makes each snapshot look almost frozen. In the background, the galaxy turns on timescales far longer still, so the whole structure travels around the galactic center while its own slow drama continues. The result is a layered impression of motion and stillness near and far, fast and slow. As the star continues to shine, its light and wind keep feeding energy into the surrounding bubble, maintaining the delicate balance between pressure and gravity in this small region of space. The present appearance of AG Carinae and its nebula is only one frame in a much longer sequence, but it already contains the imprint of past eruptions and hints of changes yet to come. From this starting point, the story can move inward toward the star's inner engine, and outward toward the wider environment that this single unstable star helps to shape. Near the central star, the outline of the surrounding bubble begins to reveal its hidden structure. The shell is not a simple smooth sphere, but a set of layered regions shaped by flowing gas and changing pressure. At intermediate distances, space around AG Carinae resembles a hollow interior surrounded by a delicately drawn boundary, like the inside of a vast, dimly lit shell. That boundary appears as a thin rim where a fast stellar wind collides with slower material that was thrown out in earlier episodes. Stellar wind here means a continuous stream of particles driven away from the star by its intense radiation. A gentle analogy is a steady river running through fog, sweeping the fog aside and building a curved shoreline from drifting droplets. In the nebula, the river is invisible while the shoreline glows where compressed gas cools and begins to emit light. The inner face of the shell traces a real physical change. Density rises across the short distance and temperature falls from blistering values closer to the star to cooler conditions in the compressed layer. Flow speed also changes, dropping where the wind suddenly encounters resistance and forms what is called a shock front. A shock front is a thin zone where fast-moving gas slows abruptly and converts part of its motion into heat. In more familiar terms, it plays a role similar to a breaking wave where an organized flow becomes churned and foamy. On the scale of AG Carinae, that wave is wrapped around the star in 3 dimensions. If this region could be seen in cross-section, it would resemble a bright ring encircling a luminous core with a darker, emptier space outside. The main number that anchors this scene is the radius of the shell, which is roughly a few light years from the star. 1 light year is the distance light travels in 1 year, comparable to several trillion kilometers. So the shell's inner wall lies far beyond any planetary orbit and deep into the realm between stars. This comparison turns an abstract distance into a more stable sense of scale, where the bubble is understood as a structure of interstellar size. Inside the shell, the rim is not uniform. Small irregularities appear as brighter knots and fainter gaps along its length, giving the impression of beads and dim valleys on a circular band. These knots form where gas has been compressed a little more strongly, perhaps where streams within the wind converge, or where older clumps of material resist the flow. Some knots trail thin filaments that stretch backward. tracing the direction of motion like faint streamers on a slow current. Light behaves differently in each of these zones. In some regions it passes almost unhindered, leaving only a gentle enhancement of brightness. In others it scatters off dust grains, giving the shell a softer, hazier glow, and lending the inner edge a pale, blurred outline. The main visual anchor here is a narrow luminous band quilted with bright beads and darker hollows suspended in a surrounding volume that remains almost completely transparent. This scene captures a small payoff in understanding. The shell is not simply the edge of an explosion, but a boundary where steady wind, older ejected gas, and cooling processes interact to build and reshape structure over time. Moving outward from this rim density falls again as the shell's thickness gives way to the more diffuse gas beyond. In that outer region, traces of the star's influence still exist, but they fade into the wider interstellar medium that threads through the Carina arm. This creates a gentle scale shift from the finely detailed boundary only fractions of a light year thick to the broad environment spanning tens or hundreds of light years around the system. Within the shell, subtle layering appears. Some arcs look slightly redder or dimmer, hinting that dust or gas composition changes from one thin band to another. These differences record earlier wind conditions, preserving times when the flow was stronger, weaker, or loaded with more dust. The shell in this sense acts like the layered walls of a canyon where each stratum marks a different period in the history of water and sediment. Filaments thread along the surfaces where these layers meet, curling in loose loops and gentle spirals that speak of turbulence long since settled into slow drift. There is a clear limit, however, to how precisely this three-dimensional structure can be reconstructed. From any single line of sight, features at different depths overlap and project into the same small patch on the sky. This means that a bright knot may hide a more distant arc or sit in front of a dark lane that appears adjacent but actually lies far behind. Resolution also imposes a boundary on intuition. Details smaller than a certain size blend together and appear smooth rather than clumpy, erasing the tiniest filaments and the thinnest gaps. To move beyond these limits, models of gas flow and radiation transport must be combined with the observed patterns of brightness and colour. Such models rely on well-tested physics but still simplify the actual complexity, so some details about the exact shapes and motions inside the shell remain uncertain. Even with these uncertainties, the large-scale picture is stable and calm. A bright star drives a powerful wind. That wind runs into older expelled material and slows, forming a curved shock where gas compresses, heats, and then cools into a luminous shell. The shell expands at high speed, yet grows only gradually on human timescales, so each image is a nearly frozen frame in a much longer sequence. Over longer intervals, the shell will stretch thin and eventually blend with the background gas of the galaxy, carrying with it the heavy elements forged inside the star. For now, it remains a defined structure, a rounded cavity with a glowing inner wall and soft internal textures that all point back toward the central source. From this layered bubble, the story can move inward to the star's outer atmosphere, where radiation pressure shapes the wind, or outward to the wider galactic environment that receives the energy and material released by this slowly unfolding event. In the deep interior of AG Carinae, energy begins its journey in conditions that never appear at the surface. The star's core is a region where light elements fuse into heavier ones, and release vast amounts of energy in every heartbeat like instant. Fusion is the joining of light nuclei into heavier ones. In this star, fusion acts as a steady engine rather than a series of explosions. It holds the rest of the star aloft in a long-lasting balance. A helpful picture is a sealed pot resting on gentle heat where steam presses against the lid without quite lifting it away. Inside the star, pressure from the intense radiation plays the role of steam, while gravity is the weight of the lid that holds everything in. Radiation pressure is the push from intense light on matter. This balance is delicate for a massive star, and small shifts in temperature or density can tilt it towards stronger outflow at the surface. The interior is not solid. It behaves more like a layered sea of hot ionized gas where deeper regions are denser and hotter, and outer regions are cooler and more rarefied. In some layers, energy moves mainly by radiation as particles of light are absorbed and re-emitted again and again. In other layers, it moves more like heated fluid in a pan as hotter material rises and cooler material sinks in the slow rolling motions. These motions create gentle stirring that mixes material and slowly carries fresh fuel into regions where fusion can still proceed. The main number that frames this engine is the star's brightness, which reaches roughly 1,000,000 times the luminosity of the Sun. A simple comparison is a single street lamp next to a vast city seen from above at night. In that view, one source overwhelms the combined glow of countless smaller ones. That extreme brightness means radiation pressure has an unusually strong influence on the structure of the outer layers. Near the core conditions are steady on human timescales, with changes unfolding over thousands of years rather than days. Yet individual particles move at high speeds and collide many times each second, while they share energy and momentum. This contrast between slow overall evolution and frantic microscopic motion is one of the most striking scale shifts inside the star. In a notional cross-section, the interior would resemble a cut fruit with a small, intensely bright centre. Around it lies a series of paler shells that fade outward. Each shell marks a zone with different temperature and density, and together they support the overlying atmosphere. Where the gradient in temperature becomes steep enough, energy transport changes character, and rising and sinking currents take over from simple radiative flow. Those currents in the upper layers can feed variations at the surface that later influence the behavior of the surrounding wind. Light that finally escapes from the visible surface has already taken a long, indirect route from the core. It has been absorbed and scattered countless times, losing the memory of its exact birthplace, while keeping the imprint of the conditions near the outer layers. In that sense, the emerging light behaves like a story retold many times that still preserves its central theme while details have been blurred. This is why much of what is known about the deep interior comes not from direct observation. Instead, it comes from models tuned to match the observed spectrum and brightness. There is a clear limit to direct measurement because no instrument can see beyond the surface of the star. Even the surface itself cannot be mapped in fine detail. At this distance, the star appears as a point of light rather than a resolved disk. Subtle changes in brightness and colour over time provide clues about internal adjustments, but those clues must be interpreted through the lens of stellar structure theory. This reliance on indirect inference marks a quiet boundary for intuition. The mind can picture shells and currents in a bright core, yet the true shapes and flows remain hidden. Despite these limits, the overall picture of the inner engine is robust. A fusion core produces energy. That energy travels outward through a layered ionized gas, sometimes by radiation and sometimes by slow motion of the material. Radiation pressure grows stronger in the outer regions and approaches a critical level where it can push back hard against gravity. That is one reason stars like AG Carinae are unstable compared with more modest stars. A small extra dose of energy or a slight accumulation of material in one layer can tip the balance and encourage stronger outflow. Over time, these imbalances feed into changes in the surface and drive variations in the stellar wind that sculpts the surrounding bubble. In the core region, distances between particles are so small that ordinary ideas of empty gas no longer apply. Matter there behaves as a continuous medium of charged particles that jostle and drift yet cannot separate very far. Pressure rises smoothly from shell to shell like weight increasing in a stack of cushions toward the floor. Closer to the centre, each cushion is more tightly compressed, even though the overall shape stays almost perfectly round. Over long spans, the balance between gravity and pressure adjusts with great care as fusion slowly changes the mix of elements. When lighter nuclei are converted into heavier ones, the way material responds to compression also changes in subtle ways. These gradual adjustments rewrite the internal profile of temperature and density but they do so without sudden jolts. The effect is more like the slow settling of an old building than a sharp collapse. Walls may shift by small amounts while the structure as a whole still stands. The inner engine therefore keeps the star from collapsing. It also sets the pace and character of the slow-motion eruptions that shape the nebula. From this interior view, the story can move outward again to the outer atmosphere. There, radiation pressure and gas pressure trade momentum and launch a powerful wind. That wind carries the star's influence into the surrounding interstellar space. Around AG Carinae, there is a thin region where the star ends and the surrounding bubble truly begins. This region is the extended atmosphere where light that fought outward from the core finally escapes and starts to push matter away as a steady flow. The transition looks simple from far away, just a bright surface and dark space beyond. Yet inside that apparent edge lies a layered zone where gravity gas pressure and radiation pressure meet in a quiet struggle. The stellar atmosphere is the thin outer layer where light escapes. Its density drops rapidly with height, so each small step outward brings a gentler pressure and a clearer path for photons. A helpful image is a deep pool where water is dense and heavy at depth but feels lighter and more open near the surface. In the atmosphere of AG Carinae, the gas near the visible layer acts like the uppermost part of that pool, already thinner, yet still held by the star's pull. Radiation pressure is the push that light exerts on matter. For a star as bright as AG Carinae, this push is not a small correction. It approaches the strength needed to counter gravity in the outer layers. At certain heights where density has fallen enough, the push from outgoing light and the pressure of hot gas together can lift material from the atmosphere and set it on a path that never returns. A stellar wind is a continuous outflow of gas from a star. In this case, that outflow forms a slow but relentless stream that rises from the higher layers of the atmosphere and accelerates outward until it joins the broader flow that shapes the nebula. The main number that sets the mood here is the wind speed, which reaches about 2,000 kilometers each second. At that speed, an object would cross the distance between Earth and the Sun in just over a day. This comparison turns a bare figure into a more grounded sense of motion. Near the star, however, the gas does not leap instantly to that speed. It starts almost at rest relative to the surface and then gains momentum as radiation pushes on atoms and ions over many stellar radii. In a mental picture, the outer atmosphere resembles a quiet terrace above a bright sea where mist hangs close to the surface. As light streams upward, it steadily nudges that mist until it forms a very slow, continuous fountain that arches away into surrounding space. The main visual anchor of this section is that luminous fountain. It rises from a thin ring around the star, not as a sharp jet, but as a soft, even curtain of glowing gas that bends outward and becomes thinner as it moves away. Closer in the gas is dense enough that collisions between particles keep temperatures high and emotions more random. Higher up collisions become rarer, and directed outward flow begins to dominate. This vertical change in behavior marks a real physical gradient, not just a convenient dividing line. As wind lifts material, small irregularities in density can grow. Slightly denser clumps feel the same radiation field yet respond differently, because their extra mass and self-gravity give them more inertia. Some fall behind while others are accelerated more strongly through gaps. Over time, these differences seed fine structure in the flow that will later appear as filaments and knots in the larger nebula. In that sense, the smooth fountain near the star already contains the blueprint for the more intricate patterns seen at distances of light years. There is a clear limit to what direct observation can reveal in this acceleration zone. No current instrument can resolve the star's surface into a disk, let alone map small-scale changes in brightness or density across that disk. Spectra show broadened and shifted lines that indicate motions in the atmosphere and wind, but they must be interpreted through models that assume certain temperature and density profiles. This means that details of how exactly the wind lifts off which patches are slightly stronger or weaker, and how small structures first form remain partly hidden. The boundary of intuition here is not in the basic picture of a radiation-driven flow which is well supported, but in the precise shapes and motions of the gas within a few stellar radii of the surface. Even with these uncertainties, the broad progression is stable. Deeper inside the star, fusion maintains pressure. Near the surface, radiation pressure climbs toward a critical level. In the atmosphere, gravity weakens with height and density falls. Beyond a certain point, the combined push from light and hot gas overcomes the pull inward. Gas then joins the outward wind and begins its long journey through the circumstellar space. This introduces a gentle scale shift from the thickness of the atmosphere, perhaps only a small fraction of the stellar radius, to the distances that the wind eventually crosses, which stretch to several light years by the time it reaches the visible shell. Time scales stretch in a similar way. The wind accelerates from near rest to its terminal speed in intervals that might be measured in hours or days for a given parcel of gas. The same gas then spends tens of thousands of years drifting through space before it finally slows and merges with the outer nebula. In that long travel, the original conditions in the acceleration zone are gradually smoothed out, yet subtle imprints remain in the density and temperature patterns that later observers can study. The atmosphere of AG Carinae is therefore not a static skin. It is an active launch zone where energy from the interior is turned into organized motion that feeds the surrounding bubble. The luminous fountain of gas rising from the star links the hidden engine in the core with the filaments and arcs far away. From this boundary region, the story can step outward with the flowing wind following it as it carves channels in the earlier ejector and builds the complex interior architecture of the nebula. In the recent past of AG Carinae, the calm bubble around the star begins with moments that are anything but calm. Giant eruptions once lifted whole layers of the outer atmosphere and threw them outward in thick, uneven waves. These outbursts are episodes of eruptive mass loss, where the star sheds material suddenly instead of through the steady wind alone. A useful way to picture them is to imagine a still pond struck by a single heavy stone. The stone hits once, yet sends a ring that travels far beyond the point of impact. In the star, each eruption plays the role of that stone, and the nebular shell is the slowly expanding ring. During such an episode, the luminosity of AG Carinae rises, and its outer layers swell so that radiation pressure gains a stronger grip on the gas. Parts of the expanded atmosphere can no longer stay bound and are lifted away as a dense outflow. The main number that anchors this scene is the total mass expelled, which may reach several times the mass of the Sun over multiple events. A comparison is a mountain losing large sections of its slope in occasional landslides rather than as a steady drizzle of dust. Each landslide is brief but leaves a thick deposit that reshapes the valley below. In the stellar setting, each deposit is made of hot gas and forming dust that carries elements forged deep inside the core. Once released, that material can never fall back into the star, and its future path unfolds entirely in surrounding space. In the same way, each giant eruption builds a new contribution to the shell around AG Carinae. Close to the star, the eruptive outflow is dense and irregular. Clumps form where gas cools slightly faster and condenses into thicker knots, while other regions remain more diffuse. These differences show up later as bright condensations and darker gaps along the shell. Some clumps move a little faster than their surroundings. They press into the gas ahead and carve small protrusions that later appear as bumps on the otherwise rounded surface. The main visual anchor here is a thick pale ring of fog expanding through dark space with ridges and hollows that never quite line up. As the outflow moves outward, it gradually thins. Pressure drops as temperature falls and the speed settles to a nearly constant value, so that the whole structure coasts away from the star. With distance, the leading edge of the flow becomes smoother, and the brightest ridges stretch into long arcs. Far behind them, faint awake-like features trail in the gas, as if the eruption has left a soft signature of its direction. The eruption itself may last only years or decades, yet the resulting shell takes tens of thousands of years to reach its present size. This contrast between short-lived events and ancient consequences marks a clear scale shift in time. On human scales, the process would be invisible as gradual drift. On stellar scales, these same eruptions are significant and even decisive. They remove enough mass to change the future evolution of the star, and they seed the surrounding space with new material. Within the shell layers from different eruptions stack on one another, like overlapping ripples on a crowded pond. Some arcs lie slightly inside others. Some appear tilted or broken where later winds have pushed them aside. These arrangements create gradients in density where one eruptive layer presses into another. At those contact zones, gas compresses further and can cool enough to form more dust, which then enhances the local brightness. Light behaves gently in these regions. It glows more strongly where density is higher and dust grains are abundant. It dims where there are gaps. It also dims where dust is thick enough to absorb and re-radiate energy at longer wavelengths that stay hidden to visible light. This gentle interplay of bright and dim patches is one clue that multiple episodes of mass loss have occurred. Yet there is a firm limit on how precisely the history of these eruptions can be reconstructed. No observer recorded the outbursts of AG Carinae as they happened. The evidence now lies only in the present shapes and velocities and compositions of the shell. Even those are measured with finite resolution and sensitivity. Many smaller clumps and thin layers fall below detection thresholds and blend into a smoother background. Models can simulate how eruptions of different strengths and durations would evolve, but they involve assumptions about initial conditions that cannot be directly checked. This introduces a quiet uncertainty into any detailed timeline. What remains robust is the broad picture. An object that is now a calm blue star inside a bubble once experienced brief periods of intense activity. In those periods, its outer layers thickened and brightened, then surged outward as heavy flows. Each flow added a new moving wall of gas and dust that joined the expanding structure. When the eruption ended, the star returned toward a quieter state while its expelled material continued outward without intervention. Over long times, the original differences between individual eruptions are softened. Layers blend where winds mix them and where shocks reshape their edges. Still, the shell retains enough structure to reveal that its origin was not a single event. It is the integrated result of several episodes spread across thousands of years. In that sense, the nebula around AG Carinae is like a hanging mobile made from many pieces. Each piece was added at a different moment, yet now moves together in a slow, graceful pattern. Seen from far away, the details blur into a simple, rounded cloud. Seen with careful instruments and interpreted through stable physics, the same cloud becomes a record of repeated, uneven breaths in the past life of the star. From this view of layered eruptions, the story shifts outward again to follow how the steady wind meets the older shells. That meeting carves broad channels and builds a complex interior filled with soft filaments inside the nebula bubble. In the inner regions of the AG Carinae nebula, gas that once seemed almost invisible begins to change character. Here, cooling flows quietly grow dust grains that will decide how light moves through the bubble. Dust grains are tiny, solid particles formed when gas cools enough for atoms to join and stay together. In this environment, they appear inside the flowing gas itself, rather than inside any long-lived cloud. A helpful picture is fresh frost forming on a quiet lake at night. At first, the surface is clear and smooth. Thin crystal patterns then spread from a few points and slowly turn the whole surface opaque. In the nebula, dust grains play the role of those crystals, and the expanding gas is the water that hosts them. The main number that anchors their scale is a typical grain size of about 1 micrometer across. This is 1,000th of a millimeter and smaller than many particles in volcanic ash. That comparison turns an abstract size into something more grounded. Each grain is far too small to see, yet taken together, they can reshape the appearance of the entire shell. Close to the inner edge of the nebula, dust abundance is still low and light passes almost unhindered. At this distance, the gas behaves like a very faint haze that only slightly softens edges. Farther out, the outflow has had more time to cool. Dust becomes more common there and starts to gather into threads. Some zones hold a little more material than others. Over long spans, these richer streaks thicken into filaments and knots, while poorer regions remain almost transparent. Collisions between grains are rare, but not absent. When two grains meet at gentle relative speed, they can stick and form a loose cluster. Such clusters scatter light in a different way and can make thin regions look brighter than their mass alone might suggest. The main visual anchor of this section is a three-dimensional frost lattice filling the bubble. Its threads are dust-rich filaments, and its nodes are brighter clumps where growth has gone farther. Pale blue, white light from the central star catches on this lattice and turns parts of it into a suspended ghostly mesh. In other places the lattice is almost invisible, and the star shines through gaps as if nothing were there. Light behaves according to local grain size and density. Shorter wavelengths scatter more strongly from small grains and give some regions a slightly bluer glow. Longer wavelengths can pass more easily through dusty zones and reveal structures hidden to simple sight. By comparing different colours from the same place, the structure of the dust becomes clearer. At small scales, there is a firm limit to direct knowledge about this lattice. No instrument can follow single grains through space. Even the sharpest image merges many trillions of particles into each point of light. This limit is a boundary on observation rather than on the process itself. To step past it, models of cuspots of condensation and gas flow are combined with measurements of colour and brightness. They use secure physics to estimate where grains should form. They also estimate how quickly grains grow. From that, they infer how grains spread through a given wind. The models are then tuned so that their synthetic views resemble real observations as closely as possible. Some details remain uncertain, yet the broad behaviour proves stable. Dust forms where gas spends enough time cooling, but is not yet too diffuse. It gathers along paths where flows converge, and at the edges of older shells left by past eruptions. Over tens of thousands of years, the lattice stretches as the whole bubble expands. Distances between its threads grow. Some clumps shear into elongated streaks while others drift apart and fade. This introduces a gentle scale shift from atoms locking together inside a growing grain to filaments that can span a fraction of a light year. It's more than travel. It also feeds back on its surroundings. Regions rich in grains absorb and re-emit radiation and can cool more efficiently than gas alone. That cooling encourages further condensation and deepens the contrast between dusty and clearer zones. Dust grains also offer surfaces where more complex molecules can assemble over long spans of time. In this way, the interior of the bubble stores material in a form that can later join wider galactic clouds. Seen as a whole, the dusty interior becomes a calm patchwork of brighter and dimmer lanes. Some regions look softly lit, others appear as dark streaks against the glowing shell. Many lie between those extremes. From far away, this fine structure blurs into a single pale envelope around a blue star. Only with careful study across many wavelengths does the inner frost lattice appear from the haze. Even then, the picture is woven from indirect clues and from simulations that fill in what images cannot resolve. The dusty heart of the AG Carinae nebula is both a product and a memory of the star's earlier activity. It records where gas once crowded and slowed and cooled. It also prepares some of that material for future use in the galaxy. From this gently structured interior, the story can move outward again. It then reaches the zones where the fast present wind meets older layers. In those regions, sharp shocks carve the bright outer arcs of the shell. Within this region, an object crossing the nebula would pass through alternating clear pockets and dusty curtains. Brightness would rise and fall in slow steps, and colours would shift with each change in grain population. The passage would feel like moving through layers of thin fog and thicker veils inside a quiet cavern. Each layer would carry a slightly different imprint of the star's history written, not in ink, but in patterns of scattered starlight. In the middle are regions of the AG Carinae bubble. The motion of gas is no longer a simple outward drift. Here the fast wind from the star catches slower layers from older eruptions and reshapes them into new structures. This is the zone of wind-shell interaction, where a present flow continually remodels the debris of the past. A helpful picture is a wide desert where steady air moves over older sandbanks and gradually sculpts them into elongated dunes. In the nebula, the fast stellar wind plays the role of air, and the older ejecta forms the movable sand. The main number that fixes the pace is a typical wind speed of about 1,000 kilometers each second. At this speed, an object would cross the distance from Earth to the Moon in less than 10 minutes. That comparison turns a remote figure into a more grounded sense of swiftness, even though the actual flows remain smooth and almost silent on their own scale. Near the inner side of the older shell, the wind strikes material that moves much more slowly. A contact surface forms where the two flows meet. Just inside that surface, the wind slows and diverts sideways, wrapping around clumps and arcs, like water that meets rough terrain and splits into branching streams. Where the wind is suddenly decelerated, a thin shock region heats the gas and increases its pressure. That hot layer then pushes on the denser, cooler shell ahead and sets it in motion. The main visual anchor of this section is a network of bright, gently curved channels carved into the inside of the shell. Each channel marks a path where the wind has bitten slightly deeper into the old material and polished the edges into smooth ridges. At some points, dense knots stand in the way of the flow. Around them, bow-shaped fronts form with their points facing the star and their wings stretching backward in long, faint wakes. These features resemble islands in a slow tidal current, with water piling up on the upstream side and streaming away downstream. Over time, the wind hollows out low cavities between these obstacles and lifts fine material into the broader flow. In cross-section, this region would resemble a shallow, irregular basin whose floor is scored by parallel grooves and whose walls carry smoother, brighter bands. The wind-shell interaction does more than change shapes. It also redistributes energy and momentum within the nebula. Gas in the wind transfers some of its motion to the older shell, so that parts of the shell are gently accelerated. Other parts lag behind. This uneven push helps to thicken some arcs, and thin others, contributing to the patchwork of brighter rims and dimmer gaps. Small variations in density become more pronounced. Where the shell is slightly denser, it resists acceleration and stands as a protruding ridge. Where it is slightly lighter, the wind pushes it outward more easily and scoops out narrow troughs. These patterns increase the contrast between adjacent regions and add depth to the interior relief. There is a clear limit to how finely these effects can be traced. Observations usually provide only the projected brightness on the sky and a rough measure of motion along the line of sight. They do not deliver full three-dimensional velocity fields. Many different patterns of flow can produce similar brightness maps. In crowded regions, bow fronts and channels overlap along the same sightline and blend into a single thin streak. Fainter cavities and smaller ridges simply fall below detection and disappear into the general glow. To reduce this degeneracy, models of wind-shell interaction are built and adjusted until their synthetic structures resemble what is seen. Yet several configurations can still fit the same data reasonably well. This limit in reconstruction is a boundary on the ability to picture the exact paths of gas. The broad conclusion, however, remains firm. A fast wind interacts with slower ejecta and sculpts channels and ridges and bow fronts inside the bubble. The scale of these structures offers a gentle shift in perspective. Some bow fronts are only a few tenths of a light-year across, comparable to a small part of the shell's thickness. The entire bubble spans several light-years, and the background arm of the galaxy stretches for thousands of light-years beyond. From a vantage inside one channel, the the nebula would feel like a shallow valley with luminous walls and a faint drifting ceiling of dust above. From far outside, those same channels merge into a thin, bright band that outlines an almost spherical halo. Timescales stretch in step with distances. The shock fronts adjust on periods that might be measured in years or centuries as local conditions change. The global shape of the bubble evolves over tens of thousands of years as the interaction region slowly moves outward. In that long process, early carved grooves may relax and fade, while new ones appear closer to the star as fresh wind catches up with older layers. Energy that once was focused in a fast, narrow wind becomes spread across a broad interior. It gently stirs and thickens the shell instead of tearing it apart. The zone of wind-shell interaction is therefore a moderating layer. It smooths the sharp contrast between a powerful central source and a quiet outer bubble. It also prepares the nebula for later stages, when the star will change character and perhaps alter its wind again. From these carved channels and bow-shaped fronts, the story can move farther outward to the thin, bright rim. There the shock-heated gas cools, and the shell radiates softly into the darkness between stars. In the outskirts of the inner channels, the gas around AG Carinae starts to show how its temperature quietly controls the way the nebula shines. In this region, hot and cooler layers sit close together in a thin band that wraps the inside of the shell. Where the gas is hottest, atoms stay ionized and glow with a sharp, clear light. Ionized gas is gas where electrons are stripped from atoms. It behaves like a responsive fluid of charged particles that react strongly to radiation. A useful picture is a wide field of cooling lava. Nearest the hidden vent, the flow still glows bright orange, while farther out it fades into dark crust and slow red seams. In the nebula, patches of gas take the place of that lava field and temperature marks where each patch sits along its cooling path. The main number that anchors this scene is a characteristic shell temperature of about 10,000 degrees. That is hotter than the surface of many ordinary stars and far hotter than any molten rock in a young planetary crust. At such temperatures, hydrogen atoms spend much of their time without their electrons. When electrons do recombine, they emit photons at very specific colours that give the nebula part of its glow. Closer to the inner side of the shell, gas remains warmer and more ionized. Farther out it cools and allows more neutral atoms and dust grains to survive. Together these layers create a quiet temperature gradient across a distance that might be only a fraction of a light year. At this distance from the starlight behaves as a patient sculptor. High energy photons penetrate the inner edge and keep gas ionized. Lower energy light reflects from dust and adds softer colors near the outer edge. The main visual anchor here is a thin luminous skin that hugs the inside of the shell. It shines brightest along a narrow rim, and then softens into fainter bands like overlapping veils of different warmth laid over the same curved surface. Within that skin, radiative cooling slowly drains energy from the hot gas. Radiative cooling is the loss of energy as light. Each photon carries away a little heat when it escapes. Over time, many such escapes allow gas to slide from hotter states into cooler ones without any sudden jumps. The process is gentle, yet its total effect is large because the shell has existed for tens of thousands of years. That span is long enough for many parcels of gas to move from a freshly shocked, very hot state to a calmer, cooler one. In some zones, the balance between heating and cooling remains almost perfect, so temperature stays nearly constant over long intervals. In others, cooling dominates and gas sinks further down the ladder of possible states. This quiet drift gives the nebula its layered appearance. There is a firm limit to how finely these temperatures can be measured. Observations often rely on a handful of bright emission lines that form at particular conditions. Those lines reveal average properties across large volumes, not the exact temperature at every point. In crowded regions, light from slightly different layers blends together before it reaches any detector. Signals from the hottest and coolest gas can merge into a single broad feature. Models must then fill the gaps by calculating how gas of given density and composition should cool and shine. They provide plausible temperature maps, but several slightly different maps can still match the same data. This uncertainty marks a quiet boundary for intuition. The mind can picture warm inner bands and cooler outer skins, yet the precise value at each location remains beyond direct reach. Even with those limits, the large-scale picture is steady. A shock front heats gas as the wind pushes into older material. Radiative cooling then lets that gas relax while the shell continues to expand outward. The hottest zones sit just behind the inner shock where fresh energy is supplied. Cooler zones lie downstream along the direction of flow and nearer the outer edge. The distance between these zones is small compared with the size of the whole bubble. Over that short span, the physical state of the gas changes a great deal. This introduces a gentle scale shift. It runs from the tiny distances where electrons change energy to the many light years of the full structure. Timescales shift in the same way. Individual atomic transitions occur in tiny fractions of a second. The shell itself evolves over tens of thousands of years. Within that interval, countless transitions have come and gone, yet their combined effect still appears as a stable glow on human timescales. From far off, the details of the temperature gradient blur into a single softly shining ring. From a closer imagined vantage inside the shell, an object would pass through layers that feel subtly different. First would come a brighter, sharper light from hotter gas. Then would follow a softer, more muted glow where dust and cooler atoms share the work of scattering and emitting. Through all of this, the bubble around AG Carinae remains calm in appearance, held in a state where heating and cooling nearly balance. From this finely layered skin, the story can move outward toward the very edge of the shell. Their light begins to leak away into the wider darkness between stars. Over the surface of the shell, the balance between temperature and ionization is not identical everywhere. Some arcs sit a little closer to the star and receive more intense radiation. Others lie behind denser filaments and spend more time in partial shadow. In those sheltered pockets, gas cools further and dust survives more easily, thickening the local veil. Over long spans, these small differences stitch a quiet patchwork of warmer and cooler lanes across the inner skin. From the viewpoint of the galaxy, this entire gradient-rich layer is only a narrow outline. It marks where energy from one unstable star meets the calmer gas of interstellar space. From far away, the nebula around AG Carinae appears almost monochrome. Closer study shows that light inside the bubble splits and scatters, giving each region its own quiet colour and brightness. Scattering is the process where light changes direction after meeting particles or irregularities. In this nebula, scattering mostly happens on dust grains and on small clumps of gas. One way to picture the effect is as a huge stained glass window held in a dark hall. The glass itself is uneven and cloudy rather than clear and flat. Some panes are thicker or more grainy, and some are thin and almost transparent. When light from the star passes through this uneven window, some rays are redirected. Some are softened and some slip through almost unchanged. The main number that anchors this scene is the diameter of the visible shell, about 5 light-years across. That distance is similar to the gap between the Sun and its nearest stellar neighbour. It turns the thin glowing rim into something closer to a wall around a tiny district inside the galaxy. Within this wall, different colours trace different physical conditions. Bluer glows tend to mark regions where scattering by small grains is strong. Redder and deeper tones mark areas where gas emits light at specific wavelengths after being excited or ionized. Emission in this sense is light produced by gas itself, rather than simply redirected. It appears where atoms have been stirred by collisions or by absorbed radiation, and then release that energy in a few preferred colours. Strips and knots that shine more strongly in those colours outline places where gas is denser or where shocks have recently passed. The main visual anchor of this section is a broad curved window in space patterned with soft patches of pale blue, gentle red, and almost colourless grey. In some places, thin dark lanes cut across that window. These lanes are regions where dust is thick enough to block a significant share of the light. At their edges, the glow sharpens because scattered and direct light overlap. Elsewhere, the rim looks smoother and more uniform, as if made from a single sheet of lightly tinted glass. Within that apparent simplicity, many subtle gradients run from inner edge to outer edge. In the inner parts of the shell, high-energy photons from the star can still reach the gas. There they keep hydrogen and other elements ionized and maintain bright emission. Slightly farther out, the same species may sit in cooler, more neutral states. There the main action of light is to scatter or to slip past without strong interaction. This short journey from highly ionized inner zones to more neutral outer skins spans a small fraction of a light year, yet the change in radiative behavior is large. That contrast marks a gentle scale shift between microscopic events and macroscopic appearance. At the smallest level, individual photons meet single atoms or grains and scatter or are absorbed. At the largest level, millions of such events blend into the smooth glow of a whole nebula seen from tens of thousands of light years away. There is a firm limit to how directly these patterns can be recovered. Images at visible wavelengths show only the front projection of the shell. They cannot separate structures that lie at different depths along the same line of sight. Two filaments that in reality sit far apart may overlap in the image and mimic a single thicker band. Some wavelengths needed to trace cooler gas and thicker dust are also absorbed by material between the nebula and the rest of the galaxy. To overcome these gaps, observations at several colours and in different parts of the spectrum are combined and compared with radiative transfer models. Those models track how light should move through gas and dust under different conditions. They are well grounded in basic physics, but still simplified so more than one model can often match the same data. This limitation defines a quiet boundary for interpretation. The large-scale understanding stays stable while small details remain open. Even within that boundary, plenty of information reaches any distant observer. The relative brightness of blue and red patches hints at the balance between scattering and emission. The depth of the dark lanes reveals where dust columns are thick. The sharpness of the inner rim shows where gradients in density and temperature become steep. Across the shell, the brightness does not stay perfectly even. Some arcs glow more strongly along directions that lie near the equatorial plane of the star. Other regions brighten toward the poles where earlier eruptions or winds have cleared wider paths through the gas. These variations sketch faint contour lines of light across the bubble, as if someone has drawn soft elevation tracks on the surface of a hill. In that view, the nebula is not a simple band, but a gently mottled shell, whose patterns remember both present winds and older outbursts. Over long spans, these contrasts tend to soften, as expansion stretches every feature and lowers the density everywhere. Over tens of thousands of years, as the shell expands and thins, these colour patterns evolve. Regions that were once bright may fade as gas cools and recombines. Other zones may brighten as fresh shocks pass through and raise local temperatures. From the vantage point of a single human lifetime, these changes are far too slow to see. On stellar timescales, they gradually repaint the stained glass window of the bubble. For now, the nebula around AG Carinae rests in a state where scattering emission and gentle absorption all share the work of shaping its appearance. From this colour-rich shell, the story can move outward into the sparser gas beyond the visible rim. It can also move inward toward broader questions about how such light patterns trace the flow of heavy elements through the galaxy. Across years and decades, AG Carinae does not stay perfectly constant. Its light and outer layers drift through slow cycles that show how close the star lives to instability. These cycles belong to the luminous blue variable phase, where a massive star hovers near a balance between gravity and radiation pressure, and sometimes tips slightly one way or the other. In simple terms, the star spends long intervals in a relatively compact hotter state, then swells into a cooler, more extended state before relaxing again. A useful picture is a giant set of bellows that opens and closes very slowly above a steady fire. The fire is the energy from fusion in the core, while the bellows are the outer layers that thicken and thin in response. The main number that anchors this rhythm is a typical brightening or dimming cycle lasting about 10 years. That span is similar to the time between two strong storms in a long climate record rather than a daily weather change. On a human timescale, it feels slow, yet compared with the age of the star, it is quite rapid. During a hotter compact phase, the radius of AG Carinae is smaller and its surface temperature is higher. Light behaves more like an intense, focused beam that presses hard on the outer layers. In these conditions, the star emits more ultraviolet radiation and drives a faster, more energetic wind. The wind becomes thinner but more forceful, carrying high speeds into the inner cavity of the bubble. In a cooler, more extended phase, the star's radius grows and its surface temperature falls. The surface behaves more like a wide, gentler lamp that still gives off enormous energy, but with a softer spectrum. The wind becomes denser and slower and can carry more mass outward, even if each particle moves with less kinetic energy. These changes in wind properties matter because they alter how new material is added to the nebula and how existing structures are pushed. The main visual anchor of this section is a pale blue lantern whose surface swells and settles very slowly. As it inflates, the glow shifts slightly towards softer colours, and the inner walls of the shell brighten in some lanes where denser wind begins to pile up. As it contracts, the colour moves back toward a hotter shade, and the brightness of those same lanes falls while more energetic radiation penetrates deeper into the inner cavity. Nearby clumps and filaments respond on their own longer timelines. They do not jump with every small change in the star, but gradually adjust as new flows arrive. Over several cycles, slight differences in wind density build up into noticeable shifts in the thickness and shape of arcs inside the shell. In some places, repeated dense phases may thicken a ridge and turn it into a long-lasting feature. In other zones, repeated fast, thin phases may hollow out a deeper channel. There is a clear limit to how directly this breathing pattern can be mapped. At this distance, AG Carinae appears as a single point of light rather than a disk. Instruments measure brightness in different colours and track how spectral lines move and change shape over time. Those line changes reveal shifts in temperature, wind speed and density, but they do not deliver a full picture of the star's surface. Gaps in historical coverage add another boundary. Observations stretch back only a little more than a century, while the star has likely repeated similar cycles for much longer. Models of stellar structure and atmosphere are used to fill the missing intervals, yet more than one pattern of internal adjustment can reproduce the same light record. This uncertainty defines a quiet limit for intuition about exactly how each cycle unfolds deep inside. Even with those limits, some solid conclusions emerge. The luminous blue variable phase is short compared with the total life of a very massive star. It may last only a few 100,000 years out of a few million. During this brief window, the balance between gravity and radiation pressure is especially delicate. Small changes in internal structure or surface conditions can launch the slow bellows motion of expansion and contraction. Each expansion makes it easier for parts of the outer layers to escape as wind or eruptions. Each contraction tightens the star and can set the stage for the next phase of its evolution. There is a gentle scale shift between short and long times here. Individual pulses in brightness take years to complete. The full luminous blue variable stage spans hundreds or thousands of such pulses. Beyond that, the entire lifetime of AG Carinae from birth to final collapse lasts only a small fraction of the age of the galaxy. In that larger context, the star's variability is a brief, intricate pattern drawn on a much longer timeline. For the surrounding nebula, the slow cycles act as a kind of clock. Density contrasts in the shell can carry faint traces of past bright and faint phases. Regions that form during denser wind episodes may be thicker and richer in dust. Regions laid down during thinner, hotter wind phases may be smoother and less massive. These differences mix with the effects of eruptions and shocks to build the full structure now seen. From far away, all these layers of history blur into a single rounded bubble around a blue point. From a closer imagined vantage, an object watching over centuries would see the lantern at the centre slowly change its size and hue, while waves of modified wind roll outward and gently reshape the inner walls. As the star continues its cycles, it moves step by step toward later stages, where its outer layers will be stripped more completely, and its inner core will become more exposed. From this slow breathing phase, the story can begin to follow that path, moving toward the transformation of AG Carinae into a hotter, more compact star that shines with a different kind of intensity. Beyond the glowing shell of AG Carinae, the wider cloud around it begins to show how one unstable star can reshape part of a galactic arm. In this region, the bubble acts like a cleared chamber carved inside an otherwise crowded field of gas and dust. The surrounding material is not uniform. It is threaded with long, faint lanes and thicker knots that belong to the general environment of the Carina spiral arm. A hollow formed by the star now sits inside that environment as a distinct pocket of lower density and higher temperature. Two main processes carry the star's influence outward. Radiation from the hot surface heats and ionizes nearby gas. The mechanical push of winds and past eruptions sweeps material aside and piles it into compressed ridges. A helpful picture is a slow bonfire burning inside a dense forest. Close to the flames, a clearing opens as undergrowth is cleared and air warms. Farther out, trees remain, but their edges are singed, and their outer branches bend away. The main number that anchors this broader scene is the size of the region that feels the star's presence, which can extend for dozens of light years along preferred directions. That span is comparable to the width of a giant molecular cloud core, where many stars might one day form. In the immediate surroundings, the bubble interior stays hotter and thinner than the undisturbed gas outside. Its inner wall presses on the outer cloud and creates curved ridges where density and pressure rise above the background. Along these ridges, small pockets can become slightly more prone to collapse under their own gravity. In other zones, the bubble simply evacuates space and leaves lower density channels, where collapse is less likely. In this way, the nebula behaves both as a sculptor and as a gatekeeper, encouraging star formation in some patches, while delaying it in others. The main visual anchor of this section is a wide, softly lit chamber opening out into a darker, mottled cloud. The chamber has a luminous inner wall, while the outer cloud shows streaks that wrap around it like the folds of a heavy curtain. At some points, the curtain is drawn close. At others, it hangs back and leaves broad gaps where hot gas can leak into more distant regions. Radiation from AG Carinae travels even farther than its wind and aging ejector. High-energy photons stream out of the bubble and carve faint, elongated zones of ionized gas along the directions where the outer cloud is thinnest. Light behaves as a cautious explorer in this setting. It penetrates easily along some lines, yet is absorbed quickly along others where dust and neutral gas are thick. The result is a pattern of bright, narrow corridors of ionization next to darker, more neutral blocks. This patchwork marks where the star's energy budget is spent and where it barely reaches. There is a clear limit to how well this large-scale influence can be mapped. Observations often sample only certain wavelengths and only at certain resolutions. They reveal emission from ionized gas and absorption by dust, but rarely deliver a full three-dimensional map. Overlapping clouds along the same line of sight can mimic a single structure. Some regions sit behind others and are hidden at visible wavelengths. To work around these gaps, astronomers combine data from radio infrared and optical bands and compare them with models of how bubbles grow inside clouds. These models assume average densities and simple shapes. Real clouds are more tangled, so several different histories of expansion and compression can still fit the same projected maps. This uncertainty defines a quiet boundary for intuition about exactly how AG Carinae has rearranged every parcel of gas around it. Even within that boundary, the broad consequences are stable. The bubble reduces density in its interior. It sweeps material into a shell and compressed ridges. It heats nearby gas and carves channels of ionized material that stretch outward along the arm. Over time, these changes alter where new stars can form and how quickly they gather mass. Some future stars may grow from gas enriched by material from AG Carinae. Others may form from gas that was pushed aside and later cools again. There is a gentle scale shift between the immediate bubble and the orbit of the star around the galaxy. The shell takes tens of thousands of years to grow and expand. The star itself needs about 200 million years to complete a single circuit around the galactic center, a period much longer than its whole lifetime. That comparison means the bubble and its parent star remain in roughly the same galactic neighborhood from birth to death. The clearing they carve in the surrounding cloud travels with them around the galaxy like a small, luminous knot on a slowly turning wheel. Over millions of years, overlapping bubbles from many massive stars can join into larger cavities. These merged structures become tunnels and chimneys filled with hot gas that connect different layers of the galactic disk. In that larger picture, AG Carinae is one contributor among many. Its present bubble fits into a wider network of cavities, shells and ridges that measure hundreds of light-years across. From far away, this network looks like a lacework of bright and dark patches draped along the spiral arm. From a closer imagined vantage within the local cloud, the AG Carinae chamber feels like a single large room opening onto a corridor of thinner gas and then back into thicker mist. At this stage in its life, the star still supplies energy to maintain the clearing. Winds continue to flow. Radiation continues to ionize gas along the easiest paths. The compressed ridges around the bubble keep their shapes while densities remain high enough. Given enough time, though, the energy source will change. As the star evolves toward hotter, more compact stages, its radiation field and wind properties will adjust. The chamber and its surrounding curtain of cloud will respond in turn. From this view of the wider environment, the story can move forward along the star's own timeline. It can follow AG Carinae as it sheds more of its envelope, exposes deeper layers and steps gradually toward the intense, stripped state known as a Wolf-Rayet star before any final collapse reshapes the region once more. Even while the bubble around AG Carinae seems calm, the star at its center continues to move toward a more stripped and exposed state. The outer envelope slowly loses mass through persistent winds and occasional stronger outflows, leaving the inner layers closer to the surface. This long transition is the path toward a future Wolf-Rayet-like phase, where the core becomes more directly connected to space. A Wolf-Rayet star is a massive star that has shed most of its outer hydrogen-rich layers. In that state, deeper zones that are now hidden will set the character of the light and wind. A useful picture is a towering storm cloud that gradually rains away its looser edges. At first, the cloud is broad and soft. As droplets fall, its outer mist thins, and a denser, darker column stands out more sharply against the sky. In AG Carinae, the winds and eruptions play the role of that steady rain. Each decade and each century removes a small fraction of the outer envelope. Over hundreds of thousands of years, those small losses accumulate until the remaining star is far more compact. The main number that anchors this future stage is a likely remaining lifetime of a few 100,000 years before final collapse. Compared with the galaxy's age of billions of years that span, is like a short evening beside a very long winter. Inside, the star fusion gradually moves from simple light elements toward heavier ones in shells around the core. Each shell burns at a higher temperature and supports its overlying layers for a shorter time. Near the surface, the change appears as a shift in the mix of elements that reach the outer layers. More helium and heavier species drift upward, while the original hydrogen-rich skin grows thinner. These composition changes alter both the wind and the light. Winds from helium-rich surfaces are usually faster and more focused than winds from hydrogen-dominated ones. Light behaves differently as well. It carries spectral features from deeper layers and spreads them into space. Over long spans, the star's spectrum slides away from that of a typical blue supergiant and approaches the harder, sharper pattern of a strip star. The main visual anchor of this section is a bright, compact ember at the centre of a large hollow sphere. Around it, the nebula shell stretches for several light years, while the star itself shrinks in radius and hardens in colour. From the nebula's perspective, the central light source becomes smaller but more intense. Its radiation field grows more penetrating at high energies. That shift subtly changes which parts of the shell remain ionized and which cool more fully. In some directions, newly strengthened winds may catch older ejecta and carve fresh channels inside the bubble. In others, the wind may become thinner and allow existing structures to relax. This evolving relationship between star and shell links their histories even as the star approaches late stages. There is a clear limit to how precisely this future can be traced. No one can watch AG Carinae through its full remaining life. Observations cover only a small part of its history, and models must extrapolate the rest. The internal structure of very massive stars remains difficult to capture in detail. Small uncertainties in how material mixes between layers or in how rotation redistributes energy can change the path toward collapse. Different model sets can predict slightly different timescales and endpoints, even when they all match current observations reasonably well. This uncertainty marks a quiet boundary for intuition. The broad direction of evolution is firm, but the exact route and timing remain open. Even within that uncertainty, some consequences are robust. As the envelope thins, the mass of the star declines. By the time a Wolf-Rayet-like state is reached, AG Carinae may have lost more than half of its original mass. That lost mass does not vanish. It resides in the nebula shell in the surrounding cloud and eventually in the wider interstellar medium. Chemical elements forged in deeper layers will be carried outward, joining the stock of material that later forms other stars and planets. This introduces a gentle scale shift from the thickness of a single burning shell inside the star to the spread of its products over many light years. Inside fusion converts matter over seconds and minutes. Outside, the same matter drifts through space over millions of years. From a distant vantage, AG Carinae's path is one example of a wider pattern. Many very massive stars pass through a luminous blue variable-like stage, and then through a stripped phase before collapsing. Their bubbles overlap, their winds phase, tangle, and their chemical yields mix in shared clouds. From a closer imagined vantage near the shell, the star's slow transformation would feel like a gradual tightening of the central glow. Over centuries, its colour would edge toward harder shades. The inner wind would gain a slightly different texture. Filaments and arcs inside the bubble would adjust with each change. Through all of this, the nebula remains a large, softly lit archive of the star's past behaviour. Its structure remembers eruptions, wind shifts, and temperature gradients long after the outer envelope that produced them has gone. As AG Carinae steps closer to a stripped state, the connection between core and environment becomes more direct. A future collapse, when it comes, will occur in a region already shaped by the star's own long preparation. From this view of this coming transformation, the story can move gently toward those final stages, where the collapse and its aftermath will send a last surge of energy and heavy elements into the already sculpted bubble and the wider galactic neighbourhood beyond. Long before any final collapse, AG Carinae already becomes a quiet source of new chemical richness for its part of the galaxy. Each wind and eruption lifts processed material from deep inside the star and sends it into the nebula and beyond. Heavy elements are atoms heavier than helium, such as carbon, nitrogen, oxygen, and more complex species. In massive stars, these elements form in burning shells close to the core and then drift outward over time. A helpful picture is a slow underwater spring feeding coloured minerals into a clear lake. The water near the spring stays slightly tinted, while the rest of the lake remains paler. Over long spans, gentle currents spread the colour everywhere. Around AG Carinae, The winds and shell ejecta play the role of that spring. The wider interstellar cloud acts as the lake that receives and slowly mixes the new material. The main number that anchors this chemical story is a total mass loss of roughly 10 times the mass of the Sun over the star's active life. That amount is enough to build thousands of rocky planets if it were condensed into solid worlds. In practice, it disperses as thin gas and dust grains across many cubic light-years. Inside the bubble, heavy elements concentrate first in the denser shell and in knots along its inner ridges. Dust grains rich in carbon or oxygen, bearing compounds grow inside cooling filaments. These grains form thin layers on the surfaces of older grains and tiny cores inside new ones. They add subtle gradients in composition across different parts of the nebula. Some arcs hold more oxygen-rich dust. Others carry more carbon-bearing material. The main visual anchor here is a layered pearl-like shell around the star. Its inner face glows with light from ionized gas, while its thicker regions carry faint, slightly different hues that hint at varied mixtures of elements. Just beyond the visible rim, the shell begins to fray into the surrounding cloud. Clumps stretch into tails. Threads break into softer streaks. Light behaves as a patient carrier in this zone. Photons from the star strike dust grains and gas atoms, knock them gently, and help spread them through subtle radiation pressure. Over tens of thousands of years, the enriched gas and dust diffuse outward. They slide along existing density gradients and follow the folds of the larger cloud. A scale shift appears between the smallest and largest parts of this process. At the microscopic level, single nuclei gain or lose particles in brief nuclear reactions inside the star. At the macroscopic level, entire enriched filaments can stretch across a few light-years and feed future star-forming regions. Timescales stretch with this shift. The reactions in burning shells may occur in fractions of seconds. The mixing of their products through the cloud can take many millions of years. There is a firm limit to how directly this chemical trail can be mapped. Observations usually measure only blended signals from many atoms along the same line of sight. Spectra give average abundances inside large volumes, not the exact path of each element. Instruments cannot follow a single atom of oxygen from its birth in the star's interior to its later role inside a planet or a small icy grain. Models must therefore trace only overall flows. They simulate how enriched bubbles expand and stir the gas around them. They assign plausible yields of different elements based on theories of stellar evolution. Different model choices can shift the exact numbers, yet all agree that massive stars like AG Carinae inject large quantities of heavy elements into their environment. Even within these limits, clear patterns emerge. Regions near the bubble tend to show higher proportions of elements forged in massive stars. Some of the gas swept into the shell may later cool fragment and collapse into new stars. Those younger stars inherit slightly different initial compositions than stars that formed from untouched gas. In that sense, AG Carinae plays a small but real role in steering the chemical history of its galactic neighbourhood. The consequences reach beyond stars alone. Dust grains that now float in the shell may one day join dense clouds that condense into planetary systems. Carbon and oxygen from AG Carinae may end up in solid crusts, icy mantles, or deep atmospheres far from their original source. This connection introduces another gentle scale shift running from the width of a dusty filament inside the bubble to orbits around future stars yet to form. From a very distant vantage, the specific contribution of one star blends into the general enrichment of the spiral arm. Many massive stars live shed mass and die over the same broad region. Their bubbles overlap and their yields mix. From a closer imagined vantage inside the shell, however, the link between core and cloud feels more direct. Heavy elements forged in the dense heart of AG Carinae now sit in thin layers of dust along its ridges and in faint gas between bright arcs. They wait in quiet suspension for the next cycle of collapse and star formation. At this stage in the story, the bubble around AG Carinae can be seen as both a relic and a reservoir. It holds a record of past outflows written in layered shells and gradients. It also stores material that will one day leave its boundaries and join the general flow of matter through the galaxy. From this view of chemical legacy, the story can move one step farther back and outward. It can place AG Carinae within the longer chain of massive stars across cosmic time and explore how many such bubbles woven together slowly change the composition of entire galactic disks. Far along the same spiral arm that hosts AG Carinae, other massive stars rise and fade, turning one region of the galaxy into a slowly changing landscape of bubbles. In this wider setting, AG Carinae is only one bright point in a loose chain of similar giants that share a common pattern of growth, loss, and collapse. Together they form a population of short-lived sources that pump energy and heavy elements into the galactic disk. One helpful concept for this collective influence is stellar feedback. Stellar feedback is the way stars return energy and matter to the gas around them. It includes radiation winds and explosive events that reshape clouds. A useful picture is a long shoreline at night lit by a series of signal beacons. Each beacon flares up, glows with varying strength and eventually fades, yet the combined pattern of light along the coast never fully disappears. It shifts as individual lamps change, but the shoreline stays outlined. In the galaxy, the spiral arm plays the role of that shoreline, and massive stars play the role of the changing beacons. The main number that anchors this broader view is the age of the Milky Way, about 10 billion years. If that span is imagined as a single long year, the full life of a massive star like AG Carinae would fit into only a brief day inside that year. During each of those short stellar days, energy output and mass loss carve structures into surrounding gas. Over the full galactic year, many such structures overlap and merge. In regions rich in gas, overlapping bubbles and shells create a patchwork of cavities, arcs, and filaments. Some cavities join into larger voids hundreds of light years wide. Their edges show curved boundaries where density and pressure rise and where new stars sometimes begin to form. The main visual anchor of this section is a face-on view of a spiral arm drawn as a ribbon of faint gas dotted with bright knots and ring-like outlines. Each ring outlines a bubble where one or more massive stars have shaped the gas, while darker streaks trace cooler, denser lanes threaded between them. Light behaves as a slow messenger along this ribbon. It reveals hot interiors at some wavelengths, cool envelopes at others, and leaves some regions only faintly mapped where dust and distance reduce signals. A gentle scale shift runs through this picture. At the smallest level, each star influences gas within a few dozen light years. At the largest level, the combined action of many such stars helps maintain the thickness, turbulence, and chemical makeup of an entire spiral arm stretching for tens of thousands of light years. There is a sharp limit to how clearly this long chain of cause and effect can be followed. Measurements of distant galaxies capture only single moments in their lives. Even inside the Milky Way data record only a narrow slice of time. Structures seen today preserve memories of stars that died long before any current light left them. Yet the identities of those individual sources are already gone. Many regions are also hidden by layers of intervening dust, and some wavelengths never reach open space from deep inside dense clouds. Models of galactic evolution therefore must rely on averaged properties. They assign typical lifetimes energy outputs and yields to entire groups of massive stars, and then follow how gas responds over hundreds of millions of years. Different model sets may choose slightly different values and mixing rules, leading to somewhat different detailed histories, even when they all reproduce broad features, such as the overall shape of spiral arms and the general distribution of heavy elements. This limit defines a quiet boundary for intuition. The large-scale pattern stays reliable, while the exact path of each bubble and each enrichment event remains blurred. Within that boundary, some steady conclusions appear. Massive stars like AG Carinae help keep parts of the disk from collapsing too quickly. Their radiation and wind stir gas and support it against gravity over large volumes. At the same time, their shells and compressed ridges create special pockets where collapse becomes easier instead of harder. In these pockets, new generations of stars may grow from gas that is already enriched. Over long stretches, this repeated sequence of enrichment stirring and renewed collapse slowly changes the average composition of the galaxy. The fraction of heavy elements rises from one stellar generation to the next. The scale shift between single star and whole galaxy carries through in time as well as space. A core collapse and its immediate aftermath unfold over seconds, minutes, and days. The influence of its ejector on future star formation unfolds over millions and billions of years. From far outside the Milky Way, this long accumulation looks like a gentle brightening and reddening of spiral arms as heavy elements build up and dust becomes more common. From a closer imagined vantage inside one arm, the same process feels like a pattern of nearby bubbles, shells, and bright knots that come and go, yet always leave something behind. In this framework, AG Carinae is one luminous step in a much longer relay. The elements forged in its core, the energy released in its winds, and the void carved by its bubble will all pass into the shared reservoir of the galactic disk. Future stars and their planets will draw from that reservoir without any direct trace of which atom once belonged to which star. The chain continues as new massive stars form live, brief, intense lives and add their own shells and beacons to the ribbon of the arm. From this wide perspective, the story around AG Carinae approaches a gentle close. The next and final turn can narrow the view, again settling back on the quiet bubble, and the surrounding dark between stars where light from many such histories now blends into a soft, steady glow. In the quiet stage of this story, AG Carinae sits inside its familiar bubble, while the galaxy around it continues on its slow rotation. The immediate scene has stopped changing in dramatic ways, yet its shapes still hold the memory of every earlier surge of energy. The nebula shell keeps its rounded outline with scalloped edges and faint knots. Inside, hot gas rests in gentle motion, drifting and eddying along invisible gradients. Outside, the wider cloud folds around the bubble like a soft landscape of hills around a shallow lake. The main themes are now continuity and release. Energy, matter, and structure all flow outward from the star and its chamber into the longer cycles of the galactic disk. A helpful picture is a lantern floating inside a broad, faintly misty valley. Close to the lantern, the mist glows and reveals fine textures. Farther away, hills and distant ridges are only outlined and remain subdued. AG Carinae and its bubble act like that lantern and valley. They cast patterns of light and shadow that gradually weaken with distance but never drop to zero. The single number that anchors this final view is the span of many millions of years over which the bubble's material will drift, mix, and eventually lose its separate identity. Compared with a human lifetime, that period is enormous. Compared with the age of the galaxy, it is a modest step in a far longer chain. The main visual anchor of this section is the Lantern Valley scene imagined from above. A soft hollow glows near the centre. Around it, layers of mist and low hills fade into darkness. Tiny bright knots mark where other lanterns also shine, scattered along the valley floor and up its slopes. In the real galaxy, those knots are other massive stars and other bubbles. Light behaves gently in this setting. It leaks out of the AG Carinae nebula, passes through layers of dust and joins the collective glow of unresolved stars and gas along the spiral arm. From far away, the detailed structure of the bubble blurs into this background sheen. One more source joins an already rich field. A quiet limit of observation appears here. No distant vantage can follow the full lifetime of a single star and its bubble in real time. Instruments record only short slices, and even those slices vary with wavelength and sensitivity. Some layers of dust hide emission at visible wavelengths. Other layers block ultraviolet photons while letting radio waves pass. To bridge these gaps, observations are combined across bands and across decades, then compared with models that evolve stars and gas under gravity and radiation. These models in turn rely on simplified prescriptions for winds mixing and turbulent flows. Small differences in those prescriptions can change the precise predicted shapes of bubbles and shells even when the overall trends stay consistent. This chain of partial views and approximations sets a soft boundary for intuition. It encourages a patient attitude toward what can and cannot be known about any single star like AG Carinae. Within that boundary, the structure around the star tells a clear story. The central object converts nuclear fuel in nested shells. It releases radiation and winds. It sheds mass in outbursts and steady flows. Those outflows carve a low-density cavity and pile gas into a shell with arcs, ridges, and knots. Heavy elements forged deep inside the core now lie in thin layers of dust and gas along that shell and in the surrounding cloud. Over time, the bubble merges into a wider network of cavities and filaments that stretch for hundreds of light years. Through this network, energy and matter from AG Carinae travel far beyond their starting point. A gentle scale shift connects three levels in this final scene. At the smallest level, individual nuclei in the star's interior continue to fuse for as long as fuel lasts. At the intermediate level, the bubble and its shell maintain their forms over hundreds of thousands of years, then slowly erode and mix. At the largest level, the spiral arm that hosts them completes its rotation around the galactic center over a few 100 million years. During that time, many other massive stars live and die, adding their own bubbles and elements to the same ribbon of gas. From a very close imagined vantage near the illuminated shell, the details of arcs, filaments, and brightness variations would stand out. Faint shadows would separate brighter ridges. Narrow gaps would open where the bubble's gas leaks into the surrounding cloud. From a mid-range vantage several hundred light-years away, the AG Carinae bubble would appear as one modest ring among many more noticeable for a moment, then slowly fading as others grow. From a far outside vantage beyond the Milky Way, the same region would blend into a smooth curve of light tracing the arm. Individual bubbles and shells would vanish into the average glow. What remains stable across all these scales is the idea that energy and matter are always being rearranged, never frozen in a single state. In the space around AG Carinae, this rearrangement takes the form of layered shells, carved cavities, and slowly drifting enriched gas. In time, every part of the present scene will change. The star will finish its fusion stages and eventually collapse. The bubble will lose its sharp boundary and merge with neighbouring cavities. The enriched gas and dust will join denser clouds that turn again into stars and planets. From the point of view of those future systems, the current bubble will be only a forgotten step. From the point of view of this calm moment, however, AG Carinae and its nebula mark a clear and gentle chapter in the long history of the Carina arm. The light that leaves this region tonight carries with it a record of that chapter. It travels outward across the galaxy and beyond, adding a quiet layer to the constantly renewing background of starlight in the universe.